Hello, everyone. My name is Konstantin Mishchenko, and I'm a PhD student in computer science working on optimization for machine learning. It is my pleasure to present today at the KAUST AI conference. The work I'm going to present to you is a collaboration with the KAUST intern Ahmed Khalid and my supervisor Peter Tarek. In this presentation, I'm going to talk about an algorithm that is used to train a wide range of machine learning models, including neural networks. So let us assume that you have a big data set, such as a large collection of images and labels. If you train a model by minimizing a certain loss function, you would likely use stochastic gradient descent, often abbreviated as SGD. In theory, SGD works by sampling data uniformly from the full dataset and updating the model to minimize the sampled loss. Here, I highlight in orange a randomly chosen data sample, which is used to perform a gradient step with respect to the random function fi of x. We repeat this process, get a new random sample, and sometimes the sample might coincide with the previous one. Why? Because we sample uniformly and forget about the past. If you now look in the long run, what's going to happen, this is roughly how it would look like. You would get new and new samples until it looks like this. And the theory of SGD tells us that it is very important to sample uniformly. In practice, however, this is not how SGD is used in most cases. What we would do to make SGD work faster is we would go over the full dataset in epochs using each sample exactly once. We would finish the epoch, and once each sample is visited, we start a new epoch and do the same thing. This is known as incremental gradient. And another alternative is when we also change the order. For every new epoch, I start with one order, get a new random order, and then get even another order, and every time I sample random permutation. This has been known for decades as a heuristic that makes SGD much faster, but in the recent years, it was realized that the theoretical convergence of this heuristic is quite different too. To explain this, let me introduce the algorithms formula and start with the problem. So we have an objective function f, we want to find a solution x in Rd, and we have n samples in the objective that we can sample from. As the function, we assume that the function is L-smooth, meaning that its gradients are L-Lipschitz, which is rather standard in optimization. So now let us explain SGD and other algorithms. SGD samples uniformly from all data samples given this chaotic order. Incremental gradient goes in a fixed order that is given to us. Random reshuffling and shuffle once go over the data using permutations. Random reshuffling changes the permutation every epoch, and shuffle once has a fixed permutation that was nevertheless sampled randomly, which is quite important for its fast convergence. The main contributions of our paper are as follows. We prove that random reshuffling converges faster than was previously thought. We show that one can use large step sizes, which is highly important in practice. We show that each iteration of the method is important through the following very simple recursion. We define the solution of the problem as x star. You define x star I using x star, and then we show that within the epoch, the iterates converge to x star I, which means that the process should oscillate during the training. And we also give a new explanation of why going in random order reduces a certain measure of variance of the stochastic gradients. So now we ran experiments on logistic regression, which showed tight match with our theory. We predicted some oscillations, and we can clearly see them in practice on this L2 regularized logistic regression problem. We also verify numerically the importance of the variance bounds that we introduced. And I particularly like the histogram on the right that shows that it is very important to get random permutations and avoid going in a predefined order, which has the largest variance of gradients shown as red bar on the right. I hope you enjoyed my presentation. Please use the link provided here if you want to read the paper and learn more. There are also contact details in the paper. Thank you for watching this.